Yes, according to the schedule, today was supposed to be, I think, biology, but then we felt that we were in the middle of the story yesterday. We were talking about the separation of mixtures, and so it would be better to continue chemistry because we had already prepared. And so is Ismail Bari with us? Ismail Bari, is he here? I cannot see him. He is not here. Okay. Okay, yesterday he was getting confused in that question. Remember, Sundus, we were discussing the quick lime and the lime water, and we had to choose the option which gives us one mixture and one. No, in which both the substances were mixtures, right? And then I mentioned that there's a question in chemistry for you that is a very good depiction. And we also discussed that a mixture, a simple way to detect if something is a mixture or not is to see if it is made up of more than one different types of particles, more than one different types of particles. Now, I'll share my screen. I want to show you that chemistry for you picture that I was talking about. Okay, this picture. Okay, can everybody see? Sundus, can you see?
Yes, yes.
Yes, okay. So this is from chemistry for you. This I think is oh, I'm so sorry. I'm so sorry. Was I muted? Oh, I'm so sorry. This is so funny. Okay. So in the last class, we were discussing what mixtures were. Remember in that question, which had in which we had to choose the option which had both the substances as mixtures. So Ismail Bari was getting confused, and then I mentioned that there was a question in chemistry for you in grade 6, and then that's a very good depiction. So I brought that question today with me in the class because I wanted to show you guys. So this is a very good picture, to clear your confusions. Now look at the boxes below. Which box contains one element only? One element only. Now look at box A. Now let's look at all the boxes together. Box A, look at box A. What sort of small particles does it have? Are all the particles same? Are all the particles same? That's my question. Are all the particles same? Who's gonna answer? Okay, Momina. Yes, Momina? In box A, are all the particles same?
Yes, they all are same.
Very good, very good. So what do you think? Is it an element? Is it a compound? Or is it a mixture?
It's a compound.
Why are you saying that it's a compound?
Because it had two atoms which were chemically bonded together and they both had different colors.
Right, because they are different in color, that means the atoms are different. Okay, Azan Kareem. This is not your Zoom ID. Now this is disturbing me, Please leave and re-enter with your Zoom ID. Who is this Azan Kareem? Do we have him here? We don't have him here. Azan Kareem, please re-enter with your Zoom ID. Jazakallah khairan. I don't want to remove you.
Excuse me, ma'am.
Yes. Yeah, you are not logged in through your Zoom ID.
What do you mean by that? I have to change my username.
Yes, the Zoom ID that I have sent you through email. Are you registered with me?
Yes, ma'am. I can't hear you.
Okay, I'm sorry. Okay, I'm sorry. I don't have time for this. Okay, Zainab 2. Zainab? Okay, let's discuss box B. Zainab, I'm trying to unmute you.
Yes, Miss, could you please show the question again?
Okay, Azan, please leave the meeting. My question is this. Tell me about box B. Do you think it is an element, a mixture of elements, a pure compound, or a mixture of elements and a compound?
It's one element because they're the same type of particles over there.
Same atom, right? Same atom, so therefore same type of particles. You're right, same type of particle. The reason why I'm using the word particle is because the particle can be an atom, the particle can be a molecule, the particle can be an ion, okay? And then even in a molecule, the molecule can be just an element in which both the atoms are the same, or it can be a molecule that has different types of atoms, in which case it would be a compound, right? Very good, Zainab. Okay, what about box C? Who will answer? What about box C? Rahim 33. Rahim 33.
Yes.
Ismail Bari, you are here with us. I want you to pay attention to this particular question. I brought this question because of you. You know that? This question. Okay, remember we were getting confused in the last class about mixtures and why, you know, quicklime was a compound and not a mixture. So I told you that a mixture is when you have more than one type of a small particles, right? So this was a question I found it very, you know, useful in for explaining this stuff. So Rahim, tell me about box C. How many types of particles do you see?
2.
In box C, how many types of small particles do you see in box C?
I see 2 particles.
2 particles only?
Yes.
Are you sure? I can see 3. I can see 3.
Yes. 3.
Okay, which ones are they? Can you tell me orally with the colors?
Like
Please.
the
Yes.
ones chemically bonded are compounds, and the ones simply alone that are elements.
Yeah, so I want you to tell me that there are 3 different types of particles in box C. There are 3 different types of particles in box C. One is, you know, in which the brown and the yellow circles are bonded together, or the brown or the yellow atoms are bonded together. And then we have brown alone and we have yellow alone. So there are 3 types of particles here. The yellow alone, 1, and then the brown alone, 2, and then yellow and brown together, which is the 3rd type of particle. So because the yellow and brown are chemically bonded together, so that's a compound. And then we have as 2 elements, brown element, yellow element, and then compound, yellow and brown, right? So this is a mixture of elements. This is a mixture of elements as well as compound, right? So this is D, I mean part D. Which box contains D, a mixture of elements and compounds? So you will write C here. Okay, now box D. Box D, Ismail Bari. Box D. Yes, Ismail. Rahim, please go ahead and
Yes.
mute yourself. Yes.
Uh,
Yes. Now tell me about box D. How many different types of particles do you see in here?
2.
Yes. Can you tell me orally which ones are the 2?
Yes.
Okay.
The orange ones or the light brown ones are elements,
Right. Very good.
and the 2 white ones that are chemically bonded are compounds.
They are compounds?
No,
Think
sorry,
again.
elements.
Right.
Because compounds
Molecular
are
element.
different arrows, chemically
Yeah, so
bonded.
they are molecules, but because the molecule is made up of same type of atom, they are molecular elements. Okay, you can call them molecular elements. So yes, there are 2
Okay.
elements. One is atomic element, the other is molecular element. Okay, but
Yes.
both are elements. So is that a mixture, Ismail? Is that a mixture? Is D a
Yes.
mixture? Why?
Yes.
What makes you say that?
Because they're different atoms.
Yeah,
Sorry,
because
elements. Yeah.
yeah, because there are different types of particles, because there's more than one type of particle,
Yes.
right? So that
Yes.
makes it a mixture. So C and D are mixtures. C and D are mixtures. Why? Because we have more than one type of particles. So C and D are mixtures. A and B are not mixtures. They are not mixtures. A is a compound. Ismail, stay with me. A
Yes.
is a compound. Now the quicklime in yesterday's question, you were getting confused that why is quicklime not a mixture? Quicklime was box A. Do you know that? Quicklime was box A. Why?
Okay.
Yeah, why? Because it was a compound. And so box A is showing us a pure compound.
Yes.
Right. And then seawater was what? Which box will represent the seawater?
Seawater is C. Sorry, D.
Seawater, yes, I agree with you. It's C. C, you know, because water molecule is a compound. Remember?
Water molecule. Okay.
Yeah. Water molecule
H2O,
is
like hydrogen and oxygen.
exactly. So that's a compound. And then we have salt in it. So we have sodium ions and chloride ions. So sodium can be brown and chloride can be yellow, right? So I think
Yes.
C will depict, yeah, C will depict seawater. Okay.
Okay.
These pictures are very helpful. Keep this picture with you, you know, for your good understanding. So I
Okay,
wanted
thank
to,
you.
okay. You can mute yourself.
Okay, thank you.
Then yesterday Sundus was talking about alloys, right? And what is an alloy? Who will tell me? What's an alloy? Alloy, fizzer. Okay. Okay, Sayyid Farzan, you are again not Farzan. See, okay, now I will rename you, but you know what? This is taking my time. And that's why, you know, I increased the time duration of the class from 1 hour to 1.5 hours. Because, you know, we cannot successfully complete any one particular topic. Okay. So yesterday we talked about alloys. Fizzer 7. Okay, I'm unmuting you. Okay, Fizzer?
Alloys are a mixture of metals.
Yes. Okay, good. Yes, alloys are mixtures of metals and basically solids into solids, where the solute is a solid and a solvent is also a solid. So both solute and solvent are solids and alloys, right? So I want to show you a picture. I'm still sharing my screen with you guys. So look at this. So can you see the darker shaded? Can you see the darker shaded and slightly bigger atoms, and the other which are slightly smaller and they are silver grayish color? So think of these darker balls as solute, okay? And these grayish silver balls as solvent. So this is a type of a mixture. This is an example of a mixture where you have solute dissolved in a solvent. Okay, so this gives it strength. I wanted to just share with you these pictures, and then let me see what other, okay. And then I also want to share with you videos of, okay, who will tell me, before I show you the video, who will tell me how does a solid or anything dissolves in water? And why is it that some substances dissolve and others do not dissolve? I want some new hand, some Abdul Wadud, okay?
Ma'am, because of the density.
Because of density? Some substances dissolve and others do not dissolve?
Yes.
No, it's not because of density. What happens when something dissolves? What happens? See, density will only explain you if something sinks or stays at the bottom, or you know, stays at the top, or you know, or remains suspended. But it does not explain dissolving. What is dissolving, first of all? What is dissolving? Okay, Smile, you tell me. Yes.
Dissolving
What?
means when you mix something where is basically when you make a solution, like you put
Yes.
salt in water and you
Yes.
can't see the salt.
So
It's
why can't you
in the
see it?
water.
Yeah, that's a very good question. Why can't you see it? See, when you are adding, you can see it, right? But when you
Yes.
stir the spoon, a time
Yes.
comes when you stop seeing it.
Yes.
So where does it go? Where does it disappear?
It's still in the water, but it's spread.
What do you mean by spread?
Like
Elaborate more. Think at the atomic level, at the molecular level. Become a molecule and then think what's happening. What's happening? Come on.
because when you add salt, when you're adding salt in the water,
Yes.
they're bonded together.
They're bonded together. Okay, you're slightly correct. Slightly correct. Okay, anybody
Because
else? Okay, Usman 50. Yes, Usman?
Yes, teacher. Some molecules have weaker intermolecular forces. So when the salt is being dissolved, so the molecules of salt just like form bonds with the water and make it dissolve.
Okay, Sidra wants to say something. Okay. Yes, Sidra.
So the reason why we cannot see salt is because the salt particles are between the molecules.
Which molecules?
The molecules of water or whatever the substance you're putting
Right.
inside is.
Right. See, when for us to see anything, particles have to be a certain size. Beyond that size, if a particle gets smaller than that particular size, we cannot see it. Okay. So for us to be able to see, particle has to have some size, right? Now, when the salt is still in the spoon, they are big clumps. Okay, so we can see them easily because they are big enough for us to see. But when we dissolve it, what happens, and I'll just show you a video, what happens is that salt gets each and every ion, each and every atom of that salt or ion, because salt is made up of cations and anions. So I will use the word ions and never say molecule of salt. That is wrong. Molecule is when two atoms are sharing electrons, and we're talking about salts here. Salt is ionic. Okay, so we have cations and anions. So these ions, they get in between the water molecule. So they are so small. Now the particles are so small, we cannot see them. That's why we feel that they have disappeared, but actually they have accommodated in between the water molecules. Okay, this is very important to understand, because if you don't understand why anything dissolves, then how will you understand how we can separate them? How can you understand the separation techniques, right? Okay, now I want to show you a video which is showing you how salt is dissolving. How salt is dissolving in water. Okay, how water dissolves in salt. So this is the video. Okay. Okay, now they will show you a salt crystal and they will show you a water molecule. Okay, just before I start this video, another thing. Do you know what polarity means? Do you know what polar molecules are? I'm sorry, before I start this video, I need to talk about polarity. What is polarity? What is polarity? Usman 50. Okay.
Yeah, teacher. Polar bonds are the bonds that are shared. Polarity is a kind of term that means that two molecules are sharing their bonds, their ions.
Two molecules are sharing their bonds.
Yeah, they're sharing their ions, positive ions and negative ions.
No, beta, no.
Covalent bonds.
Okay, let me ask Rahim 33. Yes, Rahim 33. What do you understand by polarity? What is polarity?
Polarity basically means like a molecule which is attracted to another molecule because of its different electronegativities.
Can you repeat your sentence? Your sentence has a, yeah, and please, okay, whenever you answer a scientific question, make sure that the terms you're using are exact, okay? When you're saying molecules, molecules is different from atoms, okay? Molecules are sharing, molecule meaning the whole thing. Okay, Rahim, so please say this again.
Polarity means that atoms are attracted towards another due to their different electronegativities.
Okay, Zainab. Who is it? Okay. Okay, Soman, whoever you are not signed in through your Zoom login. Please leave the room and re-enter through your Zoom ID. Otherwise, then I will have to remove you. Yeah, okay. And now I think I should log the meeting because I cannot waste my time on this again and again. Okay, I cannot, keep an eye on if the participants are. Okay. So, okay, so let me talk about polarity myself. Polarity is unequal distribution of electrons in the bond due to the different electronegativities of the atom. Like when we are talking about a bond is what? Sharing of electrons between the atoms, right? One electron by one atom, other electron from the other atom. So each atom is contributing one electron towards the bond, right? But what happens is that some atoms are more electronegative. What do I mean by electronegative is that they have greater affinity, they have greater attraction towards the electron. And so what they do is that they pull the electrons more towards themselves. They pull the electrons more toward themselves. And so there is a net negativity on that atom. And the other atom is left with less of the electrons. And therefore the other atom is left with, some positivity, right? So this is called polarity. Polarity is when within the bond, the electrons are not shared equally by the two atoms, but one pulls more than the other. And so the one that pulls more gets a negative charge, and the one that is left behind by less is left behind with a positive charge. Now, a very good example of a polar molecule is water molecule. Now, do you know which is the most electronegative element on Earth? Does anybody know which element is the most electronegative? Yes, Momina? Yes?
I think maybe oxygen.
Oxygen is number 2. There's one which is even more electronegative than oxygen. What is it? Zainab? Yes.
Hydrogen is?
Hydrogen. No way. Zainab, hydrogen is very electropositive. It's not electronegative at all. Oh, okay. Ahmad 31. Ahmad?
Yes, teacher, it's fluorine.
Very good. Which grade are you?
8.
Very good. Fluorine. Did you say fluorine?
Fluorine, yeah.
Yes, yes. Fluorine. In the periodic table, electronegativity increases towards the right-hand side, right? Electronegativity increases towards the right-hand side. So if you see, fluorine is on the top right. Electronegativity increases right and top. So fluorine is right at the upper right corner of the periodic table. So yes, oxygen is number 2, but fluorine is the most electronegative. What do we mean by it is that they attract the electrons most towards themselves. So oxygen is number 2. So, Oxygen is pretty electronegative. And so it pulls the electrons towards itself and therefore gets a partial negative charge and leaves the hydrogen atoms partially positive, right? So there is polarity, a lot of polarity in water molecule, okay? So of course it's common sense that, you know, oxygen, which has negative charge, will be attracted towards the cations of the crystals, of the salt crystals. Remember, we're talking about salt dissolving in water, right? So how does dissolving take place? I'm going to show you in the video, and in the video you will see that how the negative oxygen part of the water will be attracted towards the positively charged cation of the salt crystal, and vice versa. The positively charged hydrogen atoms of the water molecule will be attracted towards the negatively charged anion of the salt crystal. And so each cation will be surrounded by water molecules with their oxygen atoms pointed towards it, and I'll show you in the video. And similarly, the anion, which is negatively charged, will also be surrounded by water molecules, but with the hydrogen atoms pointing towards the anion, the chloride, and you know, if it's sodium chloride. Okay. Okay. So let me now share the video. He's not. Did you find? Okay. Anybody who is without the Zoom ID, I don't have time. Yeah. Okay. So now let me share this video. Okay. So this is a water molecule. The green ones are the hydrogen atoms. The blue big is the oxygen atom. Now this is salt crystal. Okay. The big pink circles are anion chloride. Okay. Anion means negatively charged. Yellow circles are cations. They're positively charged. They're smaller. Okay. So you can see now the water molecules will, the red, they're showing that this is positive. This is the positive part of the molecule. The oxygen is the negative part of the molecule. And now this is what the crystal is made up of. The salt is made up of cation and anion. Okay. The positive and the negatively charged. Okay. Now, can you see now the positively charged hydrogen atoms are surrounding the anion, and they have pulled one anion out of the crystal. Now you can see the negatively charged part of the water molecules are surrounding the cation, and so they have pulled out. Now pause. I want to pause here. Can you see the oxygen atoms are pointing towards the positively charged cation, the red color. The blue balls of the water are facing the red small ball, which is the cation. Whereas the red hydrogen atoms on the left-hand side, the red hydrogen atoms are facing the bigger negatively charged chloride ion. Can you see? Now, all these cations and all these anions will be surrounded by water molecules in similar manner. And when all the ions are surrounded by water molecules in similar manner, that's when we say that the salt has dissolved. And that's because these ions are now separate. They are so small, we cannot see them. So I hope you understood the process of dissolving. Okay, I'll complete the video. Opposite, okay. So now more ions are being pulled out. Similarly, more ions will be pulled out until all the ions are out. And they're all pulled out by the water molecules. The whole crystal dissolves. And that's when you stop seeing it, because now the particles are too small for your eyes to see. Okay, this was one good video. And then this is another video. This is also pretty good. Okay, so they're showing you a salt crystal. The small circles, the small balls are cations. The large ones are anions. The ions are called the solute, and these water molecules are the solvents. Okay, that's it. Okay. Okay, and then I also wanted to show you a real centrifugation machine. Yesterday, Sundus was talking about centrifugation. And so I thought I should show you a real centrifugation machine. So this is like, you know, this is how it looks like. And can you see the test tubes, how they are arranged in a circular manner? And then this machine rotates with real force. Now, in order to understand the physics behind centrifugation, you have to know the physics behind circular motion. So you need to know the centripetal force, centrifugal force, and how they act and everything. So we are not going to go into those details right now, but just understand that, you know, the less dense substances come at the top, and then the denser are at the bottom of the test tube. That's all for now. And then, yeah, that's that. So Sundus, now you can continue with your separation techniques.
Okay. Okay, so the last time centrifugation. So now I'm going to be talking about how to separate immiscible liquids. So like yesterday, I told you that water and oil are immiscible liquids. So one person even asked how we're gonna remove the blood and the plasma after they're layered up. So so we could use this method for that too, but this is for immiscible liquids, which are like layered up on top of each other. So the difference in physical property that we're using is the density, difference in density. So if we say that these two liquids, so this pink liquid is less dense and this one is denser, that's why it's at the bottom. We're gonna use a separating funnel to separating funnel has like a tap at the bottom. So when we open the tap, we can allow for the yellow liquid to like run off, and it just flows off. So this is how we separate immiscible liquids using a separating funnel. And now we can come to separating solids. For separating solids, there are two things we should have. That is, there should be some difference in the physical property, and it should be ground into powder. We can't use the thick lumps. We need it really fine, into fine powder. So now so I'm going to tell you how to separate using different physical properties. So the first one is density. Now, using the difference in density, we can separate the things in two ways. One is mechanical sifting. So sifting is when you like if you have sand in a pan, you move it like this. So that's sifting. And the denser the denser substance is going to move to one side, okay, because this has to do with inertia and the force that you're applying to it. So it's going to collect on one side of the pan and the sand on the other side. So people do this with river sand, which has gold flecks in it. So the gold flecks collect at one side of the pan and the sand on the other side. Now we can also use water. So the denser object will settle to the bottom, will obviously sink, and the less dense substance will rise to the surface of the liquid. So we could use, if for example we have, let's say, paper and sand, pieces of paper mixed together with sand. If we pour in water, the paper is going to rise up to the top and the sand will settle to the bottom. We can even do the same thing for plastic, which is less dense than water. So the less dense things will rise to the surface and the denser things will settle to the bottom. Then we can also use the magnetic property. And this is actually what they use in the Amazon gold digging purification. So magnets are used to clean away iron pieces from the gold. And we obviously know that whenever we can never find a substance pure on this earth. We always find it in its ore form. So because gold does not really react with any substance, it does not form compounds with any other substance, but it can have different substances attached to its surface. So if we have iron pieces on the gold, we can use a magnet to remove the iron pieces, because iron is ferromagnetic, and you can also say ferrimagnetic, both are correct. Uh, so uh, this is one way we can like remove the impurities. So impurities are anything that we don't need. So this is one way how we can remove it. So now the third property that I'm going to use is solubility. This is the most common one that we use in labs. And if, for example, we have salt and sand mixed together, we can pour in water, and that water will allow the salt to get dissolved in it. And if we let it sit, the sand will sit to the bottom, set to the bottom of the beaker, and the salt and water will remain dissolved together. Now there are two ways we can separate the sand. One is we can decant it. So we can tilt the beaker, let the sand, let the solution come into the beaker, into another beaker, so we can pour it off, and we'll get salt and water. And the sand will obviously be left behind. Or we could also use filtration. So we could filter this solution. The sand is going to remain on the filter paper because it cannot pass through. And the water, so remember, this whole solution comes down in this beaker. The salt is not going to be, the filter paper is not going to provide any hindrance to the salt. The salt, because it is dissolved with water, because it is between the water molecules, it will be able to pass through the filter paper. So it's going to be in the filtrate. The residue is going to be sand. This is the funnel, and this is the beaker. So now we can leave the sand to dry, but we still have the salt and water mixed together. And now there are again two ways we can separate salt and water. One is the most common that we have learned about in like almost every grade. We could get only the salt, or we could get both the water and the salt. So the most common one is evaporation. We can evaporate the solution, and salt would be left behind on the evaporating dish. So this is the evaporating dish, and this is the wire gauze, and this is a tripod stand. And even though in the diagram it has two legs, where we don't draw the third leg, but we know that it is a tripod stand. So even in exams, even in the IGCSE diagrams, they use two legs to represent a tripod stand. And this is a Bunsen burner. So we leave it to evaporate, and all the water goes up into water vapors, and we have the salt left behind. So, so this is pretty easy and quick, but the setback is that we only get water as we don't get water because it has turned into water vapors. So a way in which we can get water and salt, both of them back, is distillation. So distillation is kind of uses the same method, it's the only difference is that we don't let the water vapors go to waste. We condense the water vapors back into liquid water. So over here, we're in a round bottom flask. We put our salt and water solution, and we heat it up so we can use a Bunsen burner or anything, just provided heat, and at 100 degrees Celsius. So the water is going to evaporate, not the salt, because it has a really high boiling point. So the water is going to evaporate, turn into water vapors, and it'll rise up because it's less dense, so it's gas. And then it goes into this tube. So this is the thermometer where we can regulate the temperature. So we can see the temperature. We know that it's 100 degrees Celsius because this is the boiling point of water. And then the water vapors will go into this tube. As they will go through this tube, they're gonna cool down because of this water jacket, and I'm going to uh, elaborate on how this water jacket works uh, in just a second. But the water vapors, they condense because this tube is cold, okay, and they drip down into this other beaker that we have set up, and we can get it as distillate. So after we're done with this process, we get salt, like it's crusty and it is stuck to this at the bottom of the round bottom flask, and water in a separate beaker. Now, how the water jacket works is by using convection currents. So if you focus on the labelings, they always write cold water in and hot water out. So the reason why hot water is always out from this side and cold water is always in from this side is because of the fact that hot water mass rises. So because in hot water the water molecules are moving really fast, they move farther away from each other compared to the colder water. So they're farther away from each other compared to the colder water, and so they are less dense. There are more spaces between the particles. When they're less dense, they rise, so they have gotten heated up by the water vapors which are entering through this tube. So here are the water vapors, and they heated the water up, okay? So the hot water rises upwards. You can see that this is the upper side, this is the lower side because it's kept slanting, and the hot water leaves this way. The cold water is injected here because the cold water is moving less slowly, so it's more packed in together, and so it's denser, and it stays to the bottom side of the apparatus. So this is the bottom side because it's kept slanting, and over here this is where the water vapors turn into liquid, and then they drip into a beaker where we can get our distillate. So the idea that this cold water jacket uses is that hot water mass rises and leaves, and cold water remains at the lower part. So once I'm done with explaining that, I'm just going to ask you a question, and you guys can raise your hand if you want to answer. Which of the following is the best method of obtaining pure water from ink? So ink is the solute and the pure water is the solvent. Elise 45. Do you want to answer? I'm unmuting you.
Distillation.
Yes, distillation is the correct answer. It's distillation because in distillation we can get both the ink and the pure water. The ink was going to be dissolved in the solvent, so we can't decant it, okay? and nor can we filter it, and freezing is not a separation method. So distillation is the right answer. So there's and I have another question for you guys, which is kind of tricky, and I'll help you, but I would really appreciate if someone wants to do this. Which of the following substances may be condensed using a water-cooled condenser? So they have given us the different substances and the melting point and the boiling point of all four of them. We have butane, pentane, hydrochloric acid, and ammonia. So, Momina, do you want to do it?
So, if the boiling point of butane is minus 0.5 degrees
So that
Celsius,
means it's gas, right? At room temperature.
yes, it's gas at room temperature, and the water would be more. Water would be more cooler. Would be
Hotter because it's at 100 degrees Celsius. No,
yes,
at zero. It's cold water.
cold water. So it would. It would. I'm not sure whether it would condense it or not.
So it's cold water. That means it's not 0 degrees Celsius because it's not ice.
Yes.
Nor is it 100 degrees Celsius because it's not gas either. So it's cold water. That means the butane melting point. So we want it to So we want this to condense, right? Can be condensed. So we want this to condense. The boiling point is minus 0.5. And we know that the freezing point of water is 0 degrees Celsius. And we're not even talking about ice. We're talking about cold water. So cold water is going to be somewhere between 0 degrees Celsius and 100 degrees Celsius. So that temperature won't be minus 0.5. So this won't get condensed.
But the B pentane, it's plus 36 degrees Celsius, so it means at room temperature,
it's liquid.
It's liquid, so it would cool. The water would cool it.
So, but so this looks like a possible answer, but we should still go through all the options just to make sure.
HCl, hydrogen chloride, it has a melting point of minus 115 degrees Celsius and a boiling point of minus 85 degrees Celsius. So it won't be cool because the cold water would be somewhere between 0 and 100 degrees Celsius, and its boiling point is minus 85 degrees Celsius, and it's at room temperature a gas.
And then same goes for ammonia, right?
Same goes for ammonia, so the answer would be pentane.
Yes, so the answer is pentane. I hope everyone understood that. If anyone has a question, you can raise your hands. If you don't have a question, then you can lower them. Usman, 50, do you have a question?
Yes, if 36 it is room temperature and it is liquid, so why do we need to condense it? Condensation is when we change from gas to liquid.
Yeah, so basically, the question is asking us which of these substances can be condensed using a water-cooled condenser. So we have to keep the boiling point and melting point of water in mind. So it's 0 degrees Celsius and 100 degrees Celsius. So we're using water, not ice. So we know, and it's cold, which means that its temperature is between 0 and 100, somewhere here, right? We know that butane has a boiling point of minus 0.5, which means that at room temperature, which is 25 degrees Celsius, so 25 degrees Celsius is room temperature, okay? And so at 25 degrees Celsius, this is going to be gas because it has already turned into a gas at way back at minus 0.5. So at 25 degrees Celsius, it's still a gas. So if we try to condense it, so boiling point is also the condensation point. Remember the gateway analogy if you have attended the previous classes? So the boiling point is also the condensation point. So At this substance is going to condense at also minus 0.5 degrees Celsius.
Okay.
But we are somewhere between 0 and 100. So this is not going to turn into liquid because it has not reached its condensation point.
Yes.
But B, pentane, it's 36 degrees Celsius. We are somewhere between 0 and 100. 36 is between 0 and 100. So it will reach its condensation point and turn into liquid. Did you understand?
Okay. Yes. 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 Thank you.
Okay, you're welcome. Ismail Bari, do you have a question?
Yes, if a substance melting point is above 100, but like 110 degrees Celsius, so can we use water at the temperature of 90 degrees Celsius?
I don't think so. We'll need to use another substance because we need to reach its condensation point.
Okay, thank you.
You're welcome. You can mute yourself. Okay. So now we can move on. I hope there's no other question. If you have a question, you can raise your hand. Okay. So number 4 is how we can separate miscible liquids. So this, we were talking about solid and liquid mixed together. What about liquid and liquid? So for this, we're going to use the same apparatus, but we're going to have an addition, which is the fractionating column. So first of all, I don't want you to get confused by this fractionating column. And I'm going to give you a very simple diagram. So this is almost like distillation. Okay, so the same thing, and I'm going to skip the fractionating column for now. Okay, I'm going to come back to that later, but for now I just want you to understand. So let's say that we have.
Okay, so this also mentioned that, you know, these are miscible liquids, meaning liquids, not only liquid into liquid, but two liquids which dissolve into each other. You know,
Yeah.
the same dissolving mechanism that I just showed you in the video. So the two liquids that have dissolved into each other. Now, remember, okay, Sundus, also show them that diagram that you made, that picture that you made of soluble and insoluble, solute and solvent, remember? Yeah. Yeah, I wanted to show this, that, you know, on the soluble part, can you see, this is like, you know, these are the newcomers. Think of solute as the newcomer. Okay, now the newcomers have made friends, and so, you know, the old children, the children that were already there, they are playing, and, you know, like, they have surrounded the newcomers. You can enlarge your screen if you want. Okay, and, you know, on the right hand side, you can see insoluble. Here, the newcomers, which are colored yellow, are on one side. They are confined on one side. So they are not intermingling with the rest of the people. They are not making friends with the rest of the people. So what do you think? What sort of mixture is easy to separate? The insoluble or the soluble? What will be easier? What will be easier, to pull these three, you know, these three newcomers out, or to pull these three which are surrounded by the, you know, a lot of children on the left hand side? What will be easier? Yes, Abdul Wadud? Yes?
The three children who are not in between the insoluble one.
Right. Who are secluded on the right.
The right side one.
Yeah, same. Yeah. So it is more difficult to separate solutions rather than you know, suspensions. Suspension, easy. Filtration, simple. Decantation, simple. You don't need to heat, you don't need to do anything. There's no hi-fi technology behind it. You just simply filter or you decant, right? But when the two things dissolve, that's when the problem comes in. Now, how to pull them out? So we use energy, we use heat. So Sundus is now discussing fractional distillation. She is talking about separating two substances which are in the same state, meaning that they are both liquids, and they are also soluble, meaning that they are surrounded by, you know, the solute is surrounded by the solvent molecule. So it is difficult to separate. That's why we have to heat. We have to, like use all this apparatus. Okay, Sundus, go ahead. Go forward.
Okay. So the general layout for fractional distillation is almost same for like in that of distillation. Let's say we have ethanol and water mixed together, and ethanol has a boiling point of 78 degrees Celsius. Water has a boiling point of 100 degrees Celsius. So um, we are providing it heat. So there's heat, okay, and we are obviously at 25 degrees Celsius, which is the room temperature. So we're at 25 degrees Celsius, and we have to make the temperature rise from 25 degrees Celsius to 100 degrees Celsius, which is the boiling point of water. So 78 degrees Celsius will obviously be reached first, because we're going to go from 25, 30, then 40, then 60, 70, and then 78 degrees Celsius. So we're going to go gradually upwards. So ethanol comes first. So ethanol starts boiling. When ethanol starts boiling, so this is, it's going to be okay, so the red dots are ethanol, okay? So the ethanol turns into a gaseous form and then goes into this tube, and then we have the jacket right here, okay? So we have the water inlet and outlet. So the ethanol passes through this tube, and it's cold, and it condenses and drips here, drips into this beaker, and we get ethanol as distillate. So now we have ethanol out, and we're using the difference in their boiling point for this. So because it's very similar to distillation. And now we still have the water in the solution. We still have water left behind. And because the ethanol is removed, we only have water in this round bottom flask. So a question you might have is, why don't we just take this round bottom flask saying that this is water and we already got our ethanol here? The reason why we still make the water, we still boil the water off from the round bottom flask and let it drip down to another beaker is so that we can purify it further, and if there are any impurities, they will be left behind on the round bottom flask. So now we did get our 78 degrees Celsius because we have boiled off ethanol. So we're just moving on, and we still have heat being given. So, and then the water absorbs the heat, and it reaches 100 degrees Celsius, and then it boils off, okay, in form of water vapors, and goes into this tube, which is cold, and it's cold because of the cold water jacket. And then so it's still water vapor in this half of the tube, and then over here, which is the cold water inlet, it condenses into water droplets, and then it drips into the beaker, and we get the water as a distillate. So this is how we get both of our components of the solution. But so there's another question you guys might have. So in between the rise in temperature, while the temperature is rising, so like 78 degrees Celsius, if we went, so what we just did was 78 to 100, right? We made the temperature rise from 78 to 100 because we were done with ethanol and we were going on to water. So between those two temperatures, if we, for example, so we have to pass the whole range of temperature. We can't just jump directly. It's gonna heat up slowly. So if we pass like 80 degrees Celsius or any temperature in between, ethanol and water are both going to boil. So not boil exactly because as you remember, boiling is at a specific temperature at the boiling point, but they're going to evaporate. So evaporation can take place at any temperature, right? So it's also going to take place during this temperature. And while this is going on, they will still, both of them are going to rise up and get into the beaker. So in between the temperature rising, while the temperature is rising, we are going to place waste beakers at the end of our apparatus. And those waste beakers are going to contain ethanol and water because they both evaporated. So evaporation just needs a little bit of energy, and the surface molecules will get enough energy to become water vapors. So ethanol and water will become water vapors, go through the tube, and they are going to condense, and they will be collected in our waste beakers. So these are the waste beakers. We're going to just throw them away. So now coming back to the addition, which is the fractionating column.
Can you repeat this waste beaker point again? This
Okay.
waste beaker thing? Yes. So what you're saying is that between the between the boiling points of ethanol and water, at the temperatures in between, both ethanol and water will evaporate, and so then continue from there.
So both ethanol and water, when they evaporate, they are going to, so both of them are, so a mixture of ethanol and water vapors are going to enter. So there's still ethanol and water mixed up in here, and they're going to condense, and then they're going to be collected in our waste beaker, which will have ethanol and water, which is what we don't want. So we'll have a mixture of ethanol and water, and then we can just throw them away because we want only ethanol and only water.
Okay.
Okay, so then coming back to the fractionating column, the role of the fractionating column is really crucial here, and this is actually what makes it different from distillation. So the fractionating column is actually just glass beads in this
Okay.
tube.
So let's ask them, what do they know about the fractionating column? Do they know what is the function of fractionating column?
So who wants to answer? You can raise your hand.
What is the function of fractionating column? What is fractionating column for? Yes. Zainab. Okay, good.
Miss,
Yes, Zainab.
maybe some substances like boiling points would be very close to each other. So anything which is not properly like evaporated, it could go back down, or maybe it could absorb it.
Yeah.
Okay,
So
Sundus, is she correct?
yeah, she's correct. It's not only with the substances which have the boiling points really close to each other. It's with any substance, because as I told you, evaporation can take place at any temperature. So some of the other substance will also get evaporated. So let's say we want ethanol only, but the water molecules which are on the surface will get enough energy, because we're still heating it. They will get enough energy to evaporate. So this fractionating column, but there are type of,
Yeah, but also mention that, sorry. So first of all, ethanol will evaporate because its boiling point is lower at 78 degrees Celsius. Now, water's boiling point has not been achieved, but it might evaporate. So we might have we might have a few vapors of water, but we don't want it, right? We want pure ethanol and we want pure water. We don't want mixtures. That's the purpose of this. So now the fractionating column will help us in getting rid of those vapors of water. How? By condensing them. Okay, Sundus, you go ahead.
So Basically, the fractionating column is made of glass beads which have a large surface area. So the water
But finish the function first. Finish the function first. So what we are trying to, so this fractionating column will help us in getting rid of the vapors of water by condensing them back into liquid, and those drops will fall back into the round bottom flask. Okay, Sundus, go ahead.
Okay, so uh, because the water molecules, as you said, have a boiling point of 100 degrees Celsius, they have still evaporated and they are kind of sluggish and slow. So the glass beads are cold because they're far away from the heat source, right? So so that's why they're really cold and they have a large surface area. So while the ethanol can still pass through, the ethanol will pass through because it has reached its boiling point, so it's really energetic. That much energy is enough for it to turn into gas. Water is still like sluggish and it's not at 100 degrees Celsius. It has just evaporated. It's going to lose its heat to these glass beads. It's going to lose its heat to these glass beads, which have large surface area. So we're using beads for a reason, because you see there's a lot of surface area. So it's gonna lose its heat to the glass beads and it's going to drip back down into the flask where we can get it back, and ethanol will move on to the condensing and then be the distillate. So substances which have not reached their boiling point will drip back down into the flask. So that is what fractional distillation was. And I have some questions. If you guys have any questions, any confusion, you guys can ask me, then I'm going to move on to the questions I have for you.
Okay, Sundus, I have a question. Can you repeat the function of these beads and how the surface area helps it?
The beads are cold, and so because of their large surface area, uh, any water molecule passing through them will lose its energy to the beads. So the beads are
Okay.
going to absorb its energy, only its energy, not the substance. And the water will drip back down into the flask.
Why are the beads cold?
Because they're far away from the heat source.
Oh, okay. Okay. It would be interesting to find out what these beads are made up of, right? It would be interesting to
Yeah.
find out. Yeah.
I
So
think
maybe
they're
we
made
can
of
find out.
glass.
What? Sorry?
I think they're made of glass.
Okay. Grass? What?
Glass.
Glass. Right, glass. Oh, okay. Yeah. Because glass is an insulator, and so it won't take up all the heat and it will maintain its low temperature maybe.
Yeah.
And so, yeah, and so, yeah. Okay.
Zainab, do you have a question?
Yes. Can sometimes those beads be made out of a substance which can absorb other substances?
Not that I know of. No, I don't think so.
Yeah,
Okay.
because that would affect because it would, if it starts absorbing, then how would we collect, right? So that's a bad idea. Using beads made up of those substances which can absorb, that's a bad idea because it would affect, what we're trying to do here. We're trying to collect pure substances, right? Okay.
Okay.
Is there any other question? Okay, let's move on, Sundus. You go
Okay.
ahead and ask questions.
Okay, so I'm going to share my screen.
Yes, Hania?
I just wanted to ask that can you show the diagram of the fractionating column?
Yeah, okay, so I'll show you after these questions. Or do you want to see one now?
Yeah, she has already shared the screen, so she'll show you. Is there anything particular you're looking for, Hania? Or do you want to just copy it or something? Okay, move on. Sundus.
Okay. So you guys can raise your hands, and I'll unmute you. So the diagram shows the apparatus used for the slow reaction between liquid Y, boiling point 57 degrees Celsius, and liquid Z, boiling point 80 degrees Celsius. What is the purpose of the condenser? A, to be able to enable Y and Z to mix more efficiently, B, to prevent the mixture from becoming too hot, C, to allow the product to escape as fast as it is formed, D, to prevent Y and Z from escaping before the reaction is complete.
Okay, you can also enlarge your screen, you know, if you want to read it better. Yeah. Okay, so who's gonna answer? Okay, Alicia 45. Yes. Yes, Alicia.
I think it's D.
D.
To prevent Y and Z from escaping before the reaction is complete.
Okay, also discuss why A, B, and C might be wrong. Okay. Okay, Sundus, you, okay, Momina. Momina, discuss why A, B, C are wrong.
A is wrong because to enable Y and Z to affect more efficiently cannot be, because
That's not the job of the condenser.
yes,
right?
the condenser is supposed to condense the gas. B, to
Right.
prevent the mixture from becoming too hot, that is also not the job of condenser.
Right.
To allow the product to escape as fast as it's formed, that is also not.
Yeah, that's exactly the opposite of what it does.
Yes.
It does not let anything escape fast, but it, you know,
Yes.
like condenses it back.
Condenses it back. And D, to prevent Y and Z from escaping before the reaction is complete, that suits it because it is not allowing the liquid Y to escape as the reaction is happening, because boiling point for liquid Y is 57 degrees Celsius. And it is less than the boiling point for liquid Z, so it would try to escape before, but the condenser would condense it back.
Very good. Very good. Okay. For the newcomers, I'm just letting everybody know that the way we do MCQs is that we don't only tell the correct option, but we also discuss why the other options are wrong. Okay. Okay. Move on, Sundus.
Okay. A mixture of two liquids in equal proportion is fractionally distilled when the thermometer first shows a steady reading, at which point will there be the greater proportion of the liquid with the higher boiling point.
Okay, a mixture of two liquids in equal proportions is fractionally distilled when the thermometer first shows a steady reading. At which point will there be the greater proportion of the liquid with the higher boiling point? Okay, before you answer this question, I have another question. You know, they mentioned when the thermometer first shows a steady reading. So why are we waiting? Why are we waiting for the reading to get steady first? Why are we waiting for the reading to get steady first? Yes, Osman? Very good. Yes?
So
Yes?
yeah, so the reaction is finished. So that we wait till the reaction is finished.
There's no reaction going on in here. This is simple separation. Yeah, this is physical process.
So
Yeah, this is not a chemical reaction. This is a physical process going on in here. So this is simple evaporation.
After the evaporation or the whole process is finished, so then we can measure.
When does the thermometer reading get steady? When this process is going on, Usman? Remember the cooling curve, the heating curve? When was the graph flat?
when the process is finished, when the whole mixture is separated to that to study.
Yeah, you will say, you know, the way you will say, maybe you know it, but you can't say it. So the way to say it is that when the you know, phase is being changed from one to another, like in this case from liquid to gas. So at boiling point, the reading would stop until all the liquid has changed into gas. So the reason why the thermometer reading is steady is because that's where the phase change is going on, right? Yeah, I'm sure you know this, but okay. So at which point will there be the greater proportion of the liquid with the higher boiling point? Okay, let me ask, who wants to answer this question? Okay, Abdul Wadud.
Ma'am, I'm not sure. Maybe the part C.
Okay, at which point will there be the greater proportion of the liquid with the higher boiling point? Higher boiling point means that it will take longer. The lower boiling point liquid will be collected first. Okay,
So
Sundus?
part A, I think so.
Part A is the bulb of the thermometer. When the thermometer first shows a steady reading, at which point will there be the greater proportion of the liquid?
So the liquid with the higher boiling point would stay behind in the flask, right? And the liquid which has a lower boiling point will have reached its boiling point before the liquid with the higher boiling point. So the liquid with the higher boiling point is still in the flask. So the answer is C.
Very good, Abdul Wadud. Your answer was correct. C. Okay, good job.
Okay. So now the next question.
Do you have more questions on this?
Yeah, so just give me a second. So let me just share my screen.
Abdul Wadud, you have raised your hand. Is there any question you want to ask?
No, it was raised before. Sorry.
Okay.
Okay. Substance X melts at 53 degrees Celsius and boils at 100 degrees Celsius. It does not dissolve in water and it does not react with water. Which diagram shows the method most suitable for separating X from a mixture of X and water? So I'm going to show you all the...
Okay, now let's talk about the question a little bit, okay? Now, substance X melts at 53 degrees Celsius and boils at 100 degrees Celsius. That means X has the same boiling point as water. That means both of them have the same boiling point. Okay. Now, it does not dissolve in water and it does not react with water. Okay. So it will be separate from it, right? Because it does not dissolve. So it will be either settled at the bottom or maybe at the top. And it does not react with the water. Which diagram shows the method most suitable for separating X from a mixture of X and water? Now, this should be easy. Separation of such a mixture should be easy because it has not dissolved.
Okay, so the D option, I couldn't bring it in the same picture.
Okay, Momina wants to answer. Okay, Momina.
The answer would be C.
Answer, yeah, C is making sense because you see it hasn't dissolved, so you don't need.
Yes, and if we will use A, because they both have the same boiling point, they both boil together and not one substance would come out of the condenser.
Perfect. Good job. Good job. I like your thinking. Yes. Yes. Okay, Sundus, what was the D option? What was it? I mean, just tell us orally. It's okay if you couldn't bring it in here.
Okay. The D option was just heating the mixture.
Simple, on a Bunsen burner.
Yeah, so I can turn on my video and show you guys.
Yeah, it's okay. Now move on. So the correct answer is C, right?
Yeah.
Yeah. Okay. Good job, Momina.
Okay. So these are all the questions, and she wanted to see the fractionating
Okay.
apparatus. So I'll show you.
So you see, if you read the question properly and you discuss, I mean, you cannot discuss in the exam, but you know, if you read the question properly and you break it out in your mind, before even reading the options, you know the answer, you know? So that's the best way of doing a question, that read the question properly, and before even reading the option, you should know. Like, you know, don't read the option and then choose. That's a secondary quality of answer. The best way to answer is that you have the option in your mind and you're looking for that option in the options given. That's the best way. Okay.
So this is a diagram of the fractionating apparatus, and I'll show you the real one. So this is how it looks in real. You can see the glass beads.
Oh, this is the real fractionating column?
Yeah.
Yeah.
And this is how it's set up.
Okay. Yeah, the fractionating column is packed with glass beads. Okay, Abdul Wadood, you want to say something?
Yes, I did not understand the last question about this, the part C. I didn't understand.
Okay, what did you not understand? Tell me. What's your confusion?
How can we separate it? If we put the water with the X substance, it will go down with the water. It will not stay up there. So how can we separate that?
So it's saying it does not dissolve in water. So anything that does not dissolve in water will not pass through the filter paper. It will stay back as the residue.
See,
Okay.
Abdul Wadood, what makes you say that it will settle at the bottom? I mean, and then, you know, remember, filtration is a separation technique which separates immiscible solute from solvent. Immiscible, meaning that has not dissolved, okay, and preferably solid. And they mentioned that the melting point is 53. That shows that it is solid at room temperature. Room temperature is 25. So that means it is solid. Before that, before 53, at a temperature lower than 53, it is solid. So solid and it is not dissolving in water. So that means it's solid in water, and you know, it is immiscible, and therefore it can be easily separated. I mean, you don't need to, you know, fractional distillation is for two liquids which are dissolving with each other. Did you
Okay,
understand?
now I understand. Yes, now I understand. Thank you.
Okay, good. Alhamdulillah. Okay. Okay, any other question? Hania, did you see the diagram? Hania? Yes?
Yes, miss, I saw it.
Oh, okay. Okay. So are we done, Sundus? Or do you?
Yeah. Or we could start chromatography if you want, but I
No,
feel
I think, no. I think we will start chromatography in the next class. Okay, so that's the end of our class. Okay, I hope there's no question. If there's any question, you can raise your hand now. Okay, okay. Assalamu alaikum wa rahmatullahi wa barakatuh.
Allah Hafiz.